Hello, Houston. We had been talking last time about long-term memory, and we're going to continue our journey through that today. Memory is running a little longer than I had expected in looking at all the different things there are to talk about. I want to go back and make sure that we eased into the next thing that I want to talk about in an effective way. So what I'm going to do is to pick up my discussion basically on screen on the specifically with relationship to implicit and explicit memory. And I want to remind you essentially that I believe we had already defined, and I'm not quite sure where we stopped last time, but we were in the midst of getting to talking about implicit memory, which is basically defined essentially as the retention of information leading to improved task performance, not requiring conscious learning or intentional remembering. It's considered sometimes incidental learning or unintentional learning. The idea basically is that it's going on, but it's not something that you and I are consciously aware of or that we are consciously manipulating in any particular way. It can involve various things like the color of clothing that your significant other wore yesterday or this morning. Vital when you go to buy Christmas presents at the Galleria or something like that. If you're trying to match a scarf, you've got to be able to remember what his or her favorite shirt color or skirt color or what have you is. That generally is implicit learning. We don't tend to talk about it or is stored in what's called implicit memory. That is, we're not consciously aware of making those kinds of observations, but we can retrieve the information when we need it in that situation. So the features of that kind of memory are, first of all, that it's unconscious, that it's accessible only indirectly, or if you make the specific effort to do so. It's best detected or measured using various kinds of relearning or savings measures rather than overt recall or something like that. And it's unaffected usually by things like amnesia, age, many different kinds of drugs, and so forth. The length of the retention interval is basically immaterial, and interference effects don't tend to impact this unintentional learning, this incidental learning. The contrast to that is what we're going to refer to as explicit memory. That's in general what we have been talking about here and will continue to do so, though I did want to make the distinction between implicit and explicit memory. Explicit memory is basically intentional learning, recollection of previous learning or experiences. There you intended to do it. That's when you're rehearsing telephone numbers to get them from the phone book to the phone, when you're trying to learn a series of sorority sisters' names and be able to recall them at a time when you go into a sorority meeting and so forth. So in this case, the features of this memory, as we reviewed it last time, are conscious. It's accessed directly. That is, you either do or do not remember somebody's name, and you know you've got a retrieval problem if you can't recall it when you need it. It's best tested using the hardest of all measures, recall measure or recognition, and it's definitely affected by things like amnesia, age, many different drugs, the length of the retention interval, and the effects of interference, which we're going to look at in more detail here today. Some would argue that the distinctions that are made between implicit and explicit memory occur because they're based on different cognitive processes. Maybe so, maybe no. Others argue that the distinctions between implicit and explicit memory occur because they're based on independent systems of memory. And then I'm going to skip a set of material here. and move directly into, I wanted to go back, actually, and do one other demonstration that I don't think we had time to get to. I wanted to come back and just put in one more demonstration that I think will be memorable for you in terms of demonstrating what we mean by procedural memory, as I talked about that a little bit. Think of the keyboard on your computer. Put your fingers on your desktop where you are and type out for me, Paris in the spring. Think about just keys, hands on the keyboard. Remember, you're supposed to be able to do it from memory. And I noticed a number of you didn't capitalize P in Paris. It is supposed to be capitalized. Remember, you got to put that other finger down when you're typing the P. But in essence, if you think about that, that is an example of something you're retrieving directly from procedural memory. I mean, there is nothing really more procedural than running the keyboard. But if you think about it, you've got a lot of different... Could you imagine trying to describe to somebody how to type Paris in the spring? You basically got to locate the P in the upper corner there. You've got to go to the upper row to hit that. Then you've got to come to the middle row for A, go back to the upper row for R, the I, other hand, way over there. Down to the middle row for S. Space bar is the thumb. That's row 4, if you want to think about it that way. And so forth. But in essence, the sequence appears on our screen very easily, Paris in the spring. But that's an example of the complexity of some of the things that are stored unconsciously. And well, they're stored consciously, but we are unconscious, unaware of them when we use them. You and I just step up to a keyboard, and if we need to type Paris in the spring, we can sit there very easily, type it out. That is an example of procedural memory, which, as you remember then, is knowledge on how to do something that may be difficult to describe verbally. Imagine trying to describe to your 7-year-old how to ride a bike. You can't do that. You're just going to have to get out with them and run up and down the driveway to make sure that they understand the procedures that are involved there. Now, we're going to look at another section where we spend quite a bit of time here, and that is loss of memory. There are a lot of different theories as to what goes on in that process, and the work that has gone on here is fascinating in terms of its breadth and its creativity. One of my favorite studies was done by Harry Barrick, B-A-H-R-I-C-K, and his colleagues starting in the mid-1970s. And he did a fascinating examination of what has come to be known as VLTM, or very long-term memory. Harry Barrick is the one that is associated with that at Ohio Wesleyan University, and the results that he got are astonishing in the kind of study that he did. And he's talking about things that last up to half a century. We're talking really long-term, essentially permanent storage, if it can be demonstrated. And the way in which he did it was interesting. What he did was to use recall intervals that ranged from about 3 1/3 months, 3 months, 3 weeks, all the way up to 47.5 years, 47 years and 7 months, actually. And Barrick et al., that is the various colleagues that worked with him, essentially assessed high school graduates' memories for high school events and particularly people at varying lengths of intervals since graduation. That was kind of the key variable that they were manipulating there. And while there is a sharp decline in recognition that occurs and recall, in both recognition and recall, it begins to occur after about 1/3 of a century, after roughly 35 years. That may be attributable as much as anything else to the degenerative processes of aging. That is, it may not be memory itself that's flawed, but the mechanism that is trying to operate the stored or reach the stored information there. But performance levels were impressive, not only for facts, but for faces, even for figures that were learned in detail over 3 or 4 years ago, even as much as 47 years earlier. Facial recognition of former classmates was approximately 90%, even 34 years after graduation, and still at 75% even after almost 50 years. Now, the way in which he did this was rather interesting. What he did was to go into his own town's high school and go into the yearbooks way, way back, as much as 47 years back. And what he did in that situation was basically to pull out a random selection of males and females, numbering a significant number, and then he posed them to people simply in the form of, computerized pictures appearing. Do you know this person? Did you go to high school with this person? To keep them honest, What he did was to go to another Ohio town about 100 miles away, so the likelihood of overlap was quite small. And in essence, went into that yearbook, same year, different town, pulled out a comparable set of photographs, and then integrated them randomly, my high school, out of town, my high school, out of town, and so forth. And then he simply presented to the numbers or the photos to people one at a time, asking them simply to respond yes or no. Do you recognize this person? Did you go to high school with this person? And that was where those figures came from, that in essence the recall was as much as 90% accurate after a third of a century. Remember, in this case, absolute chance would be 50-50. So 90 isn't quite as impressive as it looks, but they're still pulling out 80% of the actual acknowledgments there. And so the information is just very impressive, that in fact faces can be remembered as long ago as a third of a century, and we have some likelihood, about 3/4 of a likelihood, of being able to recall a memory that is even as much as 50 years old. Truly amazing. And racks up there with the Bauer demonstration we had last week of with the proper retrieval cues, you can often identify facts that you have learned even in a rush. So there are some tricks to learning how to remember, and one of the things we'll concentrate on either in this or more likely in the next lecture is how to maximize some of the strategies. Look across what we've talked about in this section of material and then pull out some very specific suggestions for how to increase the accuracy of your ability to learn and then retain information. As an aside, I think it would also be worth noting that I keep using learning interchangeably with memory. That is not strictly correct, of course, but you can't have one without the other. It's kind of like love and marriage. Well, I won't get into that. That's a social issue. But in essence, psychologists, purely for convenience, divide learning as a kind of an input process and memory as a retention retrieval process. But they are totally interrelated with each other. That is, you cannot demonstrate learning without assuming the existence of memory, and you can't demonstrate memory without assuming that learning has already occurred. So they are really totally intertangled with each other. And it is just as a matter of convenience right now that we're looking at the memory, the retrieval process of what goes on. Two different theories about what's actually occurring in forgetting. One of these is decay. The oldest theory, the oldest assertion basically, argues that memory loss is caused in one of two ways. One, obviously, is simply decay. Okay? Question mark about that. Because of the fact that basically any of you who've done any farming or gardening will know what I'm driving at here, and that is decay is roughly analogous to erosion. Farmer plants a field and then it rains torrentially, as occasionally happens here in Houston, and all the dirt starts washing off into the stream and leaving his or her land. But in essence, that's a decay problem. It's described as decay, it's described as erosion. But the key point there is to really point out that it isn't just the passage of time that causes erosion. It isn't just the passage of time that causes decay. It is rather what goes on during that time that really is the ultimate source of any kinds of loss of information that we may experience in this kind of a situation. So in essence, one of the earliest studies of this was done by Jenkins and Dallenbach back in 1924, in which what they did was to measure the number of nonsense syllables that could be recalled after having been learned to one perfect recitation of 10 syllables. So they were given a list of 10 syllables and learned them in serial fashion. Look at one, recall the next. Look at the next, recall the third, and so forth, through all 10 with an initial recall cue to get the first syllable out. And then what they did was to measure recall up to 8 hours later. Okay, so it's a simple learn one 10-item list and then recall it 1, 2, 4, 6, or 8 hours later. What made this a creative experiment was the way in which they handled what they did for the 8 hours. And that is, what they found was that in one of the groups, they had them learn the list and then they put them to sleep. Well, they didn't put them to sleep. They allowed them to go to sleep, is perhaps a better way to phrase that. But in essence, after learning, that is, they learned the list at 11:30, midnight. And then once they had learned it, they went right on to bed at that point. So there was relatively little going on during the retention interval. If you've ever worried about what happens to you at night be aware of the fact that some number of the subjects who were awakened, as you can see on the bottom of the screen there, the dependent variable was retention interval 1, 2, 4, 6, or 8 hours later. And some of the people in the morning asked the researcher, did you actually awaken me? So that they had come up, been awakened, had recalled the information and gone right back to sleep and never recorded it. It didn't register at all in their long-term memory. But in any case, the data suggested after sleeping that there is a loss of information. Jenkins and Dallenbach attached a great deal more significance to that than many other people did. Point out here that the other condition in this case was one where the subjects learned a 10-item list and then they were basically released from the laboratory and were allowed to just go on with their everyday lives, go into biolab, go into the library and read a while, have a lunch, chat with friends, play bridge, whatever, but just normal daily activities. And then they were called back to the lab again, 1, 2, 4, 6, or 8 hours later. And as you can see, there is quite a difference in the loss of data that we see there. That is, the people who were active, who learned the list and then went back to daily living, the events of everyday life, could only recall a little bit more than 10%, 1 word in 10, of the entire list that they had learned as little as 8 hours earlier. That would suggest that long-term memory isn't particularly good. But in this case, it's probably a greater problem with the input initially, and I'll show you why here in a couple of minutes. Jenkins and Dallenbach looked at that and concluded loss of information over time, it's decay. Shut the book, published the paper, and nobody worried about it too much. Until about 30 years later, somebody else picked up that data. In fact, it wasn't even that. It was 2 decades later. Picked up that data and started looking at it, and what really hits you there when you look at that is not, well, yes, there's a significant loss over time, but the bigger thing that really should hit you there is the difference between whether you're awake or asleep. You know, you multiply by about 4-fold, 3-fold the amount of forgetting if you've been awake during the interval than if you've been asleep during the retention interval. That, in turn, led to an investigation of yet another type of hindrance with the long-term storage of information, and that is interference. Interference became the subject of another long series of studies. But in essence, the loss of information through disuse does not allow for the effects of incoming or previously learned material. The decay theory, in other words, doesn't take any account of what you've learned previously that may aid or hinder your recall. It doesn't take any account of what's going on afterwards during the retention interval. Both of those, what you've learned previously, what you learn subsequently, are potential sources of hindrance in the retention of that information that you need to retrieve right now, having learned it some period of time earlier. Interference theory makes allowance for that. That is, has room for it in terms of the effect of what you've already learned or what you learn in the time when you're trying to retain whatever information we talk about. And so basically, or whatever information you're trying to learn, this is the model that I want to propose to you right now, and we're going to come back and fill in more of it a little bit later. But in essence, this is the model that I'm essentially proposing here, and that is that loss of information does not occur just because of a single source. But if we look at 2 events that we're trying to study here, time 1 and time 2, we're going to have original learning, something we're going to learn. There's going to be an interval during which we retain this, and then there's going to be a test for recall of that information. So we learn something at time 1, we retain it for a variable interval of time, and then we spit it out. We have to retrieve it at time 2. Okay, that's the guts of what I'm going to propose here. And in essence, what is occurring is one of 2 types of things, and that is earlier learning may act forward in time to create or hinder, impede the recall of what we're calling here original learning. So we've got earlier learning that acts forward in time, potentially to hinder your ability to retrieve information that you are now trying to learn. Okay? It should also be acknowledged, although I'm not going to focus on it here right now, that we may also have what is called retroactive interference. That is, anything that occurs between when you learn something and then have to retrieve it may in fact act backward in time or somehow upset whatever has been stored as a function of that original learning. And so the second source in this model of where the interference may be coming from is the information that you take in between the time you learn something and then later need to retrieve it. give you a specific example here. Now, for now, I'm going to ignore the effects of retroactive interference, but we'll look, for instance, at, no, in fact, I guess I won't. I'll go ahead and give you the whole line here now. Let's suppose that you studied Spanish. In fact, spoke it in your home in high school, elementary, middle school, high school. You spoke Spanish, okay? Then in high school, you learned German, okay? So you spoke Spanish up until entering high school, and then you decided you wanted a second foreign language, wanted to make it European, so you studied German. That is what we're going to view in this demonstration as the original learning, okay? And then subsequently, through spectacularly bad academic advice, you decided to take French here at the University of Houston. So during the retention interval for that German that you studied in high school, you're now trying to pile French in on top of it. And so what we've set up here is an interesting test, because all of a sudden at the vacation, at the break after this session, you've been invited to go to Berlin for a couple of weeks. Your friend from high school called, invited you to go to Berlin with him or her, and so you're off to Berlin at the end of this semester. The question is, when you start trying to recall the German that you learned in high school, we have a perfect setup for assessing whether you're going to suffer from proactive interference, that is, if you're going to find Spanish words jumping in all the time, or retroactive interference, that is, every time you're reaching for das Fenster, the German word for window, are you going to be coming up with the French equivalent, the English equivalent, or the Spanish equivalent? Well, it turns out, in this kind of an experiment, the answer is crystal clear. Most psychologists would give many dollars to create this kind of a very clear result. But the answer is overwhelmingly Spanish. In that situation, if you studied Spanish in high school, you studied, in elementary and middle school, Spanish and German in high school, and French at the University of Houston, if you then go to Berlin this summer or this winter, the net result is that Spanish is going to be the major source of your interference. Those are the words that you're going to have trouble sorting out when you're reaching for the German word when you need it. So the point is that the primary source of interference in this situation is the previous learning, the earlier learning. It is, in other words, a whopping proactive interference effect. You think about that a minute. If you are a fan of baseball and have a grandparent who is also interested in baseball, I can remember my grandfather used to sit and listen to the radio. He frustrated my grandmother because he would sit outside because she didn't like baseball, so he'd get on the car radio in the late 1940s and crank it up and listen to the Red Sox games. And he would run the battery down, so my grandmother jumped in the car the next day, couldn't get it to start because of a battery problem. But in essence, in the 80s, before he died, I could talk to my grandfather about baseball, but he much preferred to jump back and talk about the Red Sox of 45 or 46 or 44 and not about the then current game or sport that he was interested in, the team that he was interested in. And what you were really seeing there was the effect of proactive interference that he was much more comfortable with. He had rehearsed it a lot longer, and it had been with him a much longer time, so that he couldn't cite for you the batting statistic of the then current star on his team, but he could talk to you about Ted Williams and his batting average year by year by year through the entirety of his career. What you're seeing there is a proactive interference effect. And so basically our conclusion in the model is that it is a whopping proactive interference effect, and it was tested by Benton Underwood in one of those studies you wish you yourself had thought of. It was an armchair study that was very simple. All he did was to go back into the literature. What he was trying to demonstrate here was the effect of proactive interference. And what he did was to go back into the literature of psychology, and he looked at all studies that involved the study of 10-item lists, all the way back into the teens and the 20s. If you learned a 10-item list and then had to recall it sometime later, that's what he plotted on this graph. And the way he did it was to basically simply, for the entire study, he simply estimated or calculated recall for a particular list and plotted it as a function of how many previous lists had been learned. So in the simplest situation, if you had learned one previous list and then recalled the instant list, what is plotted here is the recall data as a function of how many previous lists have you learned, okay? And the data is just overwhelming in terms of demonstrating the potency of proactive interference. The best single source, the highest, most easily identifiable source of forgetting for you and I, given a stable level of learning, is the amount of similar learning that we've done previously. Okay? So that what Underwood demonstrated here in this literally armchair study was a whopping proactive interference effect. That is, what the data shows you there is, if you've learned only one list previously and then have to recall a second list 24 hours later, oops, there's a labeling error on the slide there. I see that's the reason I was fumbling on my words. What should be at the bottom is number of lists, not time and hours. Okay? Number of prior lists is what should be there. That's the problem with PowerPoint. You steal a graph from one place and put it in another and then forget to change all the axis labels. But in essence, what he was looking at was percent correct responses after 24 hours, as you can see on the left axis, which is correctly labeled. Okay? So on the y-axis, it's number of prior lists. And what you see there is a whopping proactive interference effect. If you've learned only one list and then have to recall another one 24 hours later, you're 75% accurate. You can do it quite strongly. But if you've learned as few as 5 other lists prior to the one you have to recall 24 hours later, your recall is now down to about 25 or 30%. And if you have to learn as many as 20 prior lists, your recall is down not too far above chance level. Okay? You're down to about 5% recall. If you can recall the very first curve you ever saw of long-term memory permanence, it was plotted or developed by Hermann Ebbinghaus way back in 1885. And if you remember Ebbinghauss's work, what he did was to learn serial lists of nonsense syllables. He would sit in his armchair with I guess 3x5 cards, and he essentially developed what we now present either on a memory drum or more recently in a computer. And he would essentially look at a word for 2 seconds and then flip it on his tummy. Look at the next word for 2 seconds and flip it on his tummy. And just keep doing that one by one by one, repeatedly through the list. And he would do each list until he learned it one time correctly. In other words, a study exactly analogous to what Underwood has plotted in this particular set of data. And in essence, his recall a month later of 10-item nonsense syllable lists that he had learned was atrocious. It was right down about where you see this curve, although this one is actually plotting number of prior lists. But his data, after a month, mimicked this curve. And a month later, he had just atrocious recall. That's not the kind of data you want to show to people who are paying for you to go to college, because it implies that you're going to remember nothing of all this stuff that you're being exposed to. The salvation for that, and point this out very quickly to your scholarship people or your parents or you when you're working, is that the knowledge that you're studying in psychology, in sociology, in business administration, anywhere, is an integrated knowledge cluster or collection of information. And you will find, I'm sure you have now, in going through this class, that when we talk about independent, intervening, dependent variables, you talked about that way back in Intro Psych. And so in essence, there is an internal consistency to the knowledge that you're learning across the many faculty that you're exposed to. That makes the retention of that information much easier to do. Because among other things, you've got a pre-learned set of materials, which basically is a mnemonic, which we'll be looking at either later today or more likely in the next lecture. But in essence, the recall data here is so disastrously poor because of the high similarity across the many different lists that he was remembering. And it simply demonstrates the whopping effect of proactive interference. Now, in essence, the interference theory, then, is the one that's most widely accepted as the basis for forgetting of information. Tulving, back in the mid-1970s, was arguing that memories simply may not be forgotten. Perhaps they're stored somewhere, simply awaiting the proper retrieval cue. Certainly the Bauer demonstration that we did in the last couple of tapes would argue in favor of that some of you, about half of you, had 18 out of 20 after 24 or 48 hours of retention of a list of words that you had not been prepared for. So that forgetting may then become simply a failure to recall. And you can see in that situation, it would be consistent with the proactive interference explanation, because you've got so many, if you're Ebbinghaus trying to recall nonsense lists. You've got so many three-letter combinations running around in your head, you just literally can't separate them out. It's a failure of recall. Well, Tulving and Pearlstone did a study in which subjects were given lists of nouns that were organized according to categories, such as dog, cat, horse, and cow. That was the domestic mammal category. Okay, so like a subset of words that were, or lists of words that had a similar, a mediator, a common concept that they related to. Half were also given a list of categories where the names were represented within the list. That is, in addition to seeing dog, cat, horse, and cow, buried in that list would be mammal. So there was an extra hint given there in terms of the organizing feature, or a way to organize all of the items in that particular list. The biggest effect when that happened, that is when one group had simply the items and another group had the items plus the mediator built into it, the biggest difference occurred on longer lists. That is, having the category name helped or boosted recall much more significantly on the longer lists than it did on shorter lists. Having the category name was very helpful to recall. It aided recall in that situation. Mammal would be a better recall cue of a category compared to being injected or being instructed simply to recall list nouns. Okay? Recall the third list isn't anywhere near as helpful as telling you recall the list of mammals that you studied. So having that mediator is very helpful, and we're going to see that demonstrated in several different ways here in the remainder of what we look at here today. Tulving and Sotka, I always have trouble with the name, P-S-O-T-K-A, had groups of subjects that viewed anywhere from 1 to 5 words of 1 to 5 lists of 24 words. And so in essence, what we're looking at now is cue-dependent forgetting here. And what they did was to plot the number of interpolated lists, the number of lists, again, that occurred between the one that was to be learned and the one that was to be recalled. So they had groups of subjects that viewed anywhere from 1 to 5 lists, where each list was 24 words long, 3 times per list. So that's not going to lead to mastery. I mean, there's no way. You're just looking at 24 items 3 times. The lists were composed of 6 sets of 4 words in a category, such as trees, metals, automobiles, flowers, and so forth. Okay? Then there was 10 minutes of neutral activity. So you went through the lists 3 times, then you did something else for 10 minutes, and then recall. Then you were given all the category names and asked to recall as many of the words as you were capable of doing. And the data was rather interesting. The original learning, the non-cued recall, actually drops, let me show you 3 sets of curves here. Non-cued recall drops. That's what we're used to seeing. Okay? Recall the items. No help at all as to the constituent names of what's in the list. That's non-cued recall. And that is very typical of what we see relative to original learning. That is, mastery of the list was up around 18 out of the 24 words that were learned. So original learning was up about 75% after 3 recitations. Non-cued recall, the standard, give me the information, as you can see, drops substantially. Even in 10 minutes, you're already down to about 50%, actually less than that, almost 40% recall. But cued recall is essentially as good as the original learning was. That is, if you were given the elements, the constituent elements, the concept label of what it was you were trying to recall, the recall was much better in that situation. With the cues there, the recall was simply much more effective in that particular kind of situation. If I can get my notes apart, we can go to the summary. Forgetting is caused by a change in retrieval information, not by the loss of memory traces. Okay? If you have the retrieval cue, the information is likely to be there. Witness again the Bauer demonstration that we did last week, last tape, where we showed you, we asked you to recall something unique to your own generation strategy, and yet you were able to go 20 out of 20, remembering having recited the word once, and then you were right on. I was doing them about once every 5 seconds, and yet you were still able, after thinking about it only 5 seconds, to retrieve it 2 days later, minimum. So restoring recall cues, I'll get it out in a minute here, restoring recall cues restores missing information to learners' cognitive environment, is the conclusion of the investigators here. So now we've basically come full circle, if you think about it. What we're saying is that information that is stored at the time of storage is crucial to the ability to recall it. That is, in that situation where the recall name or the category name is buried within the material to be learned, it aids in the recall of that information when that cue is given to you later. So the recall cues must have that information. They must have buried within them the kind of information that you're looking for in attempting to retrieve long, extended lists of information. Now, finally, we're going to get into strategizing, looking at the strategies that we use for memory. We're going to discuss and review the details of the various strategies for improving the efficiency, adequacy of our long-term memory. It's an invaluable aid, as you would acknowledge, to improving our grades in school, successes in meeting and recognizing people, and being able to call their names when you need them. And we'll see that there are a variety of things that impact our ability to actually do that. One of the things we're going to look at here in terms of memory strategies is what is called the total time effect. This is not the pronunciation time effect. You may remember that we looked at this in our previous one of the previous tapes. I showed you that if you read these 6 names, it takes much longer than it does if you read these state names. And in fact, your ability to recall was, I never actually asked in class here, but I'll bet you that in fact your ability to recall names of states when you read them was much higher on this list than it was on the longer list. And in essence, the point was that you can remember about 1.5 seconds of auditory information in sensory store, in the auditory sensory store. And in essence, that is not what I'm talking about here. Okay? What we're talking about instead is what's called the total time hypothesis. So it's not the pronunciation time hypothesis, which I was talking about previously, but rather the total time hypothesis. It demonstrates that the total time you take to master material will, within limits, be a constant. You have to think about that a minute, because I'm going to show you how to spend that time. And in essence, what the total time hypothesis is arguing is that the amount learned depends on the cumulative time devoted to the learning, called the total time hypothesis. And in fact, it is stable enough that it is often referred to in the literature not as a hypothesis, but as an effect, the total time effect. Okay? It is, however, I should point out, also important how you spend that time. That is, what the quality of time is, what you're doing during that time. We talked about how to study way back on day 1 or day 2 here. Having the radio on in the background, the TV on in front of you, and the cognitive psych book in your lap is not quality time interacting with Matlin's cognitive psych text. Okay? There's a lot of interference being created there. And you'll remember, it's in the prior learning situation. It's setting you up for proactive interference when you're listening to the radio as you're trying to learn. What you do during the time spent does determine how much of what you learn will be recalled when you need it. The more time you spend learning material, the better you will know it within limits. There is a declining benefit of overlearning. There are studies, which I won't go into, that demonstrate if you give somebody a list of 10 words and run them to one perfect recitation, what can be done then is studies that base it on percent of overlearning. So if it took you, say, 10 trials to learn a 12-item list, we'll give you 20 trials, that's 100% overlearning. You had it for twice as long as, and 50, 75, doesn't matter. There is a declining benefit from continuing to overlearn. Okay? If you reach 100% mastery, and then we look at your recall over an extended period of time, the benefits of the extra time that you spend decline. So basically, the lesson there, in combination with the total time effect, is to suggest that what's best is to simply spend quality time during the time that you do spend studying material. This leads directly, though, to the other point that I want to make here, and that has to do with what's called the distributed practice effect. And this is something that you should learn, because it's going to alter the way in which you will organize your study time. Okay? All other things being equal, it is broadly true that distributed practice is better than massed practice. Much better. And I emphasize the much. Okay? Research documenting that goes way back into the 1950s. It's half a century old. One investigator by the name of Benton Underwood has almost 35 consecutive Roman numeral studies looking at massed practice versus distributed practice, and in all but one of those studies, it was quite clear that distributed practice is better. In terms of the total time hypothesis, what do I mean by that? What I mean is, let's just pick a number here out of imagination to make the point that I want to make. And that is, let's suppose that in learning a 12-item list of moderately meaningful material, it takes you 10 minutes to master it. Going through it one at a time, it takes you 10 minutes to master it. Okay? What is being argued in the mass practice effect is that in essence, that's your practice. That's the mass practice you're spending on it, is that 10 minutes. Distributed practice would suggest that what you do instead is to study the list for 5 minutes now, wait an hour, and study it 5 more minutes. In other words, you take the total time, but you split it up. Same total time with the list, but you don't learn it all at once. You don't overburden yourself in that way. That kind of an effect, that is taking the same amount of time and spreading it out over time, is a more powerful learning vehicle, and it aids in recall for a variety of different reasons. First of all, if you've thought about it for a while, you've learned it in time one, and then thought about it again later, what you've got is time to form linkages between the two, between the various materials that if you've had time to think about it, in other words, you've got time to form associations between the various components of the material you're working on. Now, a 5 versus 10 minute example is trivial in terms of the second point, but that is that what you also do is to eliminate tiredness between study sessions. I think you can amplify and figure out that what I'm talking about by parallel is 2 hours of studying versus an hour now and an hour tomorrow, or something like that. But in essence, the rest between has the benefit of giving you time to think about it, but it also gives you time to recover from whatever tiredness or boredness developed in mastering the material. So you've got more time to think about the material and form links. And finally, studying material for shorter intervals means that you're fresh when you're studying it. So instead of having 1 2-hour stretch, by the end of which you are bored, you're thinking about the next thing you'd rather be doing or the last thing you were doing, by separating it with 2 intervals of 1 hour, you have eliminated or maximized several of the effects that eliminated is the key word, that were hindering your ability to return to learn in distributed practice, in mass practice. I'll get it out eventually. Think about the way you study courses. What you tend to do is be driven by exams. You remember the literature in Intro Psych on the effects of fixed intervals, and you remember that produces in rats a scalloped performance curve. You remember that, okay? A month between exams, and what happens in rate of study is it goes up, and then you have the exam, and you don't study it for a week afterwards. So it goes up again just for the next exam, and you've got what is called a scalloped performance curve, okay? The basis for my introductory psychology text, which is an electronic one, is to have forced deadlines through the entire semester. The idea being that what we do is to level out student studying, so that instead of having this mass of knowledge that you're trying to master in a cramming session just before the exam, if you're only going to put 6 hours into the course getting ready for an exam, it is much better to do it an hour a week than it is to do it 6 hours the night before between 8 a.m. and between 8 p.m. and 2 a.m. That is mass practice. Distributed practice is better. And if you don't believe me, go look up Benton J. Underwood, Journal of Experimental Psychology. Pick any of 36 studies, and it will be demonstrated for you that distributed practice is better. So the distributed practice effect is essentially arguing in favor of spreading your time out. What I'm arguing is that instead of studying organic chemistry on Monday night, algebra on Tuesday night, and geography on Wednesday night, it would be better and smarter to study an hour of organic on Monday, Tuesday, and Wednesday, an hour of geography on Monday, Tuesday, and Wednesday, and an hour of whatever else I said, algebra, on Monday, Tuesday, and Wednesday. Distribute the practice. And then we get into another rather interesting issue, and that has to do, drilling home the point again, distributed practice is better than massed practice. Period. Point made. Okay? One of the things we then start looking at is, well, okay, on what basis are these various kinds of learning is going to take place. And in essence, one of the issues that crops up is the issue of imagery. When you and I are trying to remember, certainly the long-term memory study that was done at Ohio Wesleyan is very clearly imagery-based, because you may be able to think back about what friends looked like in their yearbook picture, but that's an image in essence that you're recalling, or is it? The issue of imagery, as opposed to learning of words, has led to a significant amount of research, and it relates to the following kind of situation. That is obviously a picture. I happen to like that. I throw that into my introductory lecture a couple of times just because I think it's a spectacular picture. It doesn't relate to anything I'm directly talking about, but it does in fact raise the very interesting question, and that is a picture worth 1,000 words? The old saying. And the answer, research-wise, data-wise, is most clearly yes, it is. Look at the detail in that picture. Can you see houses on the back shore there, on the shore behind you? You have the wave that is thrown up behind the young lady who's cutting that turn. Okay? If you look at the wave itself, however, you notice that there are two different sources of that wave. Clearly, to her left side of the ski is what's causing all of this splash, if you look at it, because she's cutting a pretty sharp corner there. And in fact, all of this behind her has been caused by the throwing of the water off that same side. The ski is just planing across the water there and throwing it to the side. Is she happy or sad? Probably happy, but it's a look of considerable concentration on her face. What color is she wearing? Does she have a life vest on? And so forth and so on. Is it windy that day? A little bit. The water is not absolutely smooth by any means, or you'd see a reflection of her, and so forth. All of that is features that are drawn out of those pictures. And in fact, if I were to show you that picture in any later tape in the course and ask you, have you seen it before, the answer will definitely be yes. But if you think about all the features of that picture that I've pointed out to you, there is clearly a verbal encoding that is possible about this. Skier cutting to the right, big splash to the left, shore behind, rope in front, what is it, a green-handled ski tow bar, I think there, handlebar, and so forth. But all of that is just stored very easily in that image. Kinesio and Haber in 1970 did a very interesting study in which what they did was, if you can believe this, they showed subjects 2,560 pictures at the rate of 10 a second. You work that out, and those subjects spent, because they were looking at them for 10 seconds each, they spent the equivalent of about 8 hours, not quite, but 8 hours looking at pictures. 10 seconds each, 6 a minute. Click, click, click. Later, in a recognition test, what was stunning about that result was that the subjects could recall 93% of the pictures. That is, they could, is it in a yes-no on pictures that were integrated with the others that they were looking at. They were 93% accurate in tagging pictures that they had previously looked at in 8 hours for 10 seconds each. A stunning feature of memory. The answer then is very clearly that one picture is worth 1,000 words, and perhaps many more than that if we were actually able to precisely quantify it. Now, the rapid rate of presentation in that study makes it highly unlikely that the recall was verbal in that situation. There just isn't enough time to process and verbally convert 2,500 plus pictures at the rate of 10 seconds apiece. It's just not enough time. And even if you were to grant me that could occur, we're then stuck with the proactive interference effect that we demonstrated for you earlier, which is a verbally based process, not a picture-based process. So you've got the demonstration of very high recall, first of all, and then a demonstration of the difficulty of recalling similar amounts of verbal information. And it becomes quite clear that we have to be using images to a certain extent. Coslin, Ball, and Reiser did another very interesting study in which what they did was to create a map and then put on that map various kinds of distances. Okay? Now we're going to have to take my picture off the screen here in a minute to see the next thing which I'm going to offer you, which is a rail map of the Western Pacific Railroad going from San Francisco to Reno. Unfortunately, it didn't project. I had this all done on Old English type so that it really looked like it was 100 years old, because I actually drew this from the map of the railroad going from San Francisco to Reno. But the kind of study that was done by Coslin and colleagues was basically to create a map like this and then have various distances right on the map itself. And in essence, if you were asked to imagine the trip or to estimate the time from here to Livermore, it might be about 32 miles. Okay, that one was drawn out of memory. I was on leave at Stanford one year, and I think I remember that being about the estimated mileage. The other one I looked up to be sure. But that is a quicker recall for you than is something like, okay, how far is it to Verdi? Just a little bit shy of Reno. And in that case, the actual answer is 179 miles, but it turns out the ability to answer that takes longer. Can you explain that verbally? And the answer is clearly no. That what you've had to do there is serially process the information, the map, and to think to yourself, if you're familiar with the trip, let's say, okay, Oakland, Alameda, Livermore, Lathrop, Elk Grove, Sacramento, Junction, Newcastle, Colfax, Alta, Cisco, and so forth. I mean, you're not going to do it that literally, but implicitly that's what your brain is having to do, is to make the entire run along those railroad tracks, picking up the names as you go, and thus estimating the distance from the one to the other. So that in essence there we have an example of the importance of imagery. And this, to drill the point home here, is a study that was done a number of years ago that looked at, by Alan Pavio, actually, a person who was one of the first to introduce the idea of imagery. This was done back in the 70s, and it was very controversial at the time, because psychology was very heavily in the behavioral mode at that point, and people were unwilling even to concede that things like images existed in our head. And he had to do very fundamental studies, such as what I'm about to show you here, where what he would do is to take nonsense syllable lists and in some cases and pair them with simple three-letter trigrams that were meaningful. Okay, so he would have cat or dog as a stimulus term when he was using a high imagery-based word, and he would have XAG or something like that when he was using a low imagery value term. All right, and the data that he found was of the following type. If you were learning a 12-item list, number of correct responses after you've learned it and are asked to retain it is as indicated there on screen. If you have a high imagery value stimulus word like cat or dog and a list of response terms, remember this is a paired associated learning task, in the recall situation, the recall will be close to perfect when you have high imagery value stimulus term and high imagery value response term. It's not as good, but still a respectable 3/4 if you have high imagery value stimulus term and low imagery value response term. So it is harder to recall the nonsense syllables, the same interference effect that we talked about earlier. But look at the difference that the imagery value of the stimulus term makes when we compare recall in the low imagery value stimulus condition. Low imagery value stimulus, when it's a high imagery value response, still has you performing at only a little bit better than half of the list after a common retention interval. And if both of the items are of low imagery value, that is the worst ability to recall of all, a little less than half after the standard retention interval. To make the point in another way, look at the two middle groups as they're graphed there. The average amount of imagery value for the second group, the HL group, is exactly the same as the average imagery value of the materials in the LH group. The difference there is in the high imagery value, when you have a split between high imagery and low imagery value terms, you clearly want to have those that create an easy image for you as the stimulus term in that situation, because exactly the same list, if you reverse stimulus and response terms, you end up with a tougher recall. it is demonstrating, among other things, the value of imagery, because that was the only thing that differed in these terms. They had essentially the same association value, the same ease of linkage in terms of the words themselves, but the difference was in the imagery value of the recall cue that was utilized there. Concentrate on and remember the effect between second list and third list there, because that really drives home the value of imagery and the fact that it is operating, because there was no other difference between the low and the high imagery value lists except the imagery value of the terms themselves. Imagery is being used by us under certain situations. Get ready, because I'm going to read you a story of the following type. With hock to gems financing him, our hero defied all scornful laughter, which tried to prevent his scheme. Your eyes deceive, he had said, an egg, not a table, correctly typifies our unexplored planet. Now 3 sturdy sisters sought proof, forging along sometimes through calm vastness, yet more often over turbulent peaks and valleys. Days became weeks, as many doubters spread fearful rumors about the edge. Now 3 sturdy at last from nowhere, welcome winged creatures appeared, signifying momentous success. Write down as many words as you can remember out of that 75-item story. Okay, judging from looking around the room and the number of pens that aren't wiggling, I'll assume that you're near the end of ability to recall there. Let me show you the results under that condition. On screen, we'll put the graph in a minute or two. There we go. That's the recall data that you get under 3 different conditions of syntactic constraint. This was an experiment done by Lackman and Dooling, okay, in which what they did was to manipulate 2 different things, and I'm about to apply the second variable for you here. But in essence, what they showed you, first of all, was English words in a variety of what is called constrained conditions. The English that I'm speaking, what you're writing, is constrained. That is, their subject has to follow verb and so forth and so on. The rules of dictation, of speaking English, are dictating what's going on. So in the order that I read it to you, you actually heard it in a condition called high syntactic constraint. That is, it was standard English. Okay? Another condition involved taking clusters of words, 2 or 3 in a phrase, and randomizing them. So you might get with hock to gems buried somewhere in the list, but it wasn't going to be at the beginning where it was in my recitation. It would be somewhere down in there. And under low syntactic constraint, it was entirely randomized. Okay? You had the words just coming out in any particular order. And as you can see there is a very slight effect of adding constraint, that is, of adding English order to what was otherwise a random list of words. Okay. Now, I'm going to give you one additional hint, if you want to think about it that way. I'm going to give you a title. So in the absence of a title, we're up to about, 15 words recalled, even under the condition that you heard it. Now I'm going to give you one additional hint. Think about it in that context. With hock to gems financing him, our hero bravely defied all scornful laughter which tried to prevent his scheme. Your eyes deceive, he had said, an egg, not a table, correctly typifies our unexplored planet. Now 3 sturdy sisters sought proof, forging along sometimes through calm vastness, yet more often over turbulent peaks and valleys. Days became weeks as many doubters spread fearful rumors about the edge. At last, from nowhere, welcome winged creatures appeared, signifying momentous success. Now, I won't ask you to rewrite the words. But what are three sturdy sisters? Ships, of course. Can you name them? The Nina, the Pinta, and the Santa Maria, and so forth. So all of these other things come in to aid your recall in that situation, and it shows up in the data. Also, if we look back at the graph, look at what happens when you add the benefit of a label. Recall goes from at the extreme, in the best of all conditions under the green curve, what you're looking at there is 75 English words in standard English order with the benefit of the label Columbus, which allows you to picture turbulent peaks and valleys, becomes the ocean, and so forth. Welcome winged creatures are the doves, the seagulls that flew out to join them, and so forth. So that in essence you lend a great deal of additional meaning in what is essentially there an advanced organizer. But buried within that is another important fact, and that is look at recall under the red condition. That is where you have no order at all. You're just listening to 75 words read in any order and no label at all. And the ability to recall under that condition is about 12, a little bit less than 1/6 of all the material is recalled. If you add to that simply order, same words put in standard order, and add a label to it, what is called an advanced organizer, it increases recall by 50%. You're now up to 18 words correct. And again, keep in mind, what's plotted there are 6 different routes. Obviously, I squandered you as a research group by putting you in the high syntactic constraint, no Q condition. So we couldn't ask you in fairness to recall. But in essence, in that situation, the label has done a lot, as has the order of the materials. It lends to the imagery that can be generated, and it also provides a mediator, a way in which you can tie all of the material together. So in essence, the advanced organizer clearly has facilitated recall in that particular condition. The issue here then is the memory that is involved an analog memory or not? A photograph is an analog. That photograph that we looked at earlier is an analog image, okay? For every part of the image, there is a portion of your sensing apparatus that is stimulated, and it can be represented there. You could pick any particular splash of water on there, and those of you watching in high definition will be able to pick out. You could isolate that dot of water if you wanted and pay attention to it, okay? But there are any of a number of different dots that you could pay attention to in that analog image. Every aspect of the image there is paralleled somewhere in the stored image within our memory at this particular point. But this becomes a hotly debated issue in experimental psychology, and that is essentially, is there something in long-term memory that is essentially an equivalent to a visual perception? That is, that includes with all its individual details. Let me give you a tease as to why this may be the case. How many of you have ever seen a holographic image, a photo image of a true three-dimensional object? Anybody in the room? It's amazing. The technology was quite rampant about 10 years ago. But in essence, what you have, if you have a piece of film that's like so big, like 18 by 18 or something, if you bend it and light it just right, suppose you've got a picture of, well, I don't know, let's say a mouse, to give us something we can talk about here. You have a picture of a mouse, three-dimensional in all its glory, on the screen there. If it's a holographic image, a true three-dimensional image, the result is that if I roll around to one side and look at it, I'm losing details on the far side of the mouse as I'm gaining details on this side of the mouse. And by the same token, if I roll around this way, looking only at a three-dimensional image of that mouse, I gain details on this side, the crack between the left and right buttons, the cable and where it comes out, and I'm losing information around on the back side of the mouse, so that it is a true three-dimensional image. My parallel is suggested in the following way. What do you think happens if we take that great big image and cut a quarter of it? So now we've got a piece of film that's this big. Bend it just right, light it properly. what are we going to see in that film? Still 3D, yes. You're not on the mic, but we'll give you credit. You're still in 3D. But how about the image? It's going to be smaller. And if you were to pull it apart or expand it, it won't be as detailed. You have lost some of the details in that situation. One investigator at Stanford has actually suggested that. Well, in fact, let me give you the parallel. Remember, we had a print this big. If it was just a regular photograph, an analog, we cut a quarter of it, and we cut it just right. We've got a quarter of the mouse still there, but we don't have the full picture. We've got same detail on a smaller portion of the picture. Okay? With the holographic image, what happens is that when you reduce the image size, or the negative size, and then project it, what you end up with is a fainter, vaguer is the better word to use, representation of whatever image is pictured in that situation. Okay? The parallel that has been suggested is that may be a good parallel to the way memory is stored in our head. The point being that the image, the mouse itself in that big picture of a mouse is stored everywhere on the film. It is put on the film in what's called a helical scan, which you don't need to worry about. But the effect of it is to spread the digital bits of representing that thing all over the film. And the result is the image of that thing in the negative, the traditional Kodak negative, there it is, different goofy color, but there it is. In the negative out of which the three-dimensional photographs are made, the holographic images are made, it is literally spread across the entire film. So if you take a smaller version of it, you still have a complete pool of information in that smaller film with which to create a slightly less good quality image of the entire thing. The parallel in memory is a fairly strong one. The idea being that images are stored, words are stored, knowledge is stored, not in one place. There is not an apple neuron in your head. You don't recall the word apple from a given place. It's not a single neuron that represents all the things we know about apple. But rather, you assemble the information from a lot of different places when you're trying to recall the image. And the suggestion is, in fact, the parallel information is people who have war injuries, who get a portion of their head blown away in battle, or drug effects where a certain amount of the brain has lost function, or injuries, cancer, anything like that, where some distinct, demonstrable portion of the frontal or parietal cortex is destroyed, you don't suddenly lose the word for peanuts. You don't suddenly lose the word for apple or anything else. You don't lose the nouns. You don't lose verbs. You don't lose anything except processing speed. What it does is to take you, the more significant the injury, within limits, the slower, the longer it will take you to respond and pull the word that you need in a given situation. So there is, in the basic physiology of our brains, some degree of parallel to be concerned with, enough to warrant justification with things like looking at holistic images of stored information, such as the picture that we were looking at. Now let's look at this and pose the following problem to you. First of all, I want to sound a caution for you. The question here that we're debating about in terms of image versus storing of words is not about anything involving imagination. There's no doubt that we imagine things. We know that's going on. But consider thinking about the most efficient way to do the things that you had to do this morning to get here, or tonight if you need to be here at 7 for an exam, or something like that. Do you recognize this image? Is there anybody that does not recognize the image? Okay, I'm pleased for you. This is Houston, okay, with all the routes and interstates labeled. Your problem is the following. We know where the U of H is located, but your difficulty is that sometime before you get to school here, you've got to visit the Galleria, see your dentist way up in northwest Houston, get your car serviced, pick up the laundry, get milk at the grocery, and reach U of H in time for a 7 p.m. exam. This is not the way to do that. Going to the dentist, then the garage, then the groceries, then the Galleria, then the cleaning, and then coming to the U of H. You'll waste a lot more gas. You've crossed your own path about half a dozen times there, and you put yourself on a lot of roads that are not going to facilitate your movement around the city. So there is significant benefit to you and I to being able to conjure, think in holistic terms. And so what we tend to do is to not do it that way. We instead do it something like, okay, Galleria, then the garage is close, dentist is furthest out of the way, but it's on the way if I'm going back to the cleaners, and then to the groceries, and then to the U of H. And so in essence, in that way, we have gone in linear fashion by minimizing the distance between each of those target areas. Now, you may not do that formally in your head. Well, you do it formally in your head, not perhaps as systematically as I've shown you here, but that is essentially what's going on when you face the kind of goals that I cited for you there. And it's not an unreasonable set of what you might have to accomplish any given day, but you maximize your efficiency in using some kind of a three-dimensional image. You may have to be graphically challenged enough that you have to lay out a map to do the work, to figure it out. But in fact, you can do that. Now the question is then, was this information retrieved from visual memory, or was it reconstructed from a verbal memory? That is essentially the battlegrounds. No doubt images do exist. We've just shown you several sets of data that will document that. But the second issue here, the other caution that we should sound is that what is the functional equivalent of images and visual perception? That's a tough one. Is the image, such as the picture of the young lady water skiing that I showed you earlier, does that have any direct parallel in our head to the perception that we generate off the surface of our eye when we look at that picture of the lady water skiing? And the issue then is to try to identify the memory representation. Is it identical to a visual perception? Is our perception of a scene the same as the visual, the memory, the storage of it? Okay, and we have to argue that if we can set up experimental situations in which imagery would most likely be used, then does the performance reflect the limits we'd expect in terms of movement around or use of a visual image? That's a lot of words, but essentially what I'm saying is that if we're going to try to demonstrate the difference between a semantic representation and a visual representation, what we're going to have to do is set up some kind of a task that clearly involves an image that we can specify in some way, that we can identify with and understand exists there. And then what we're going to have to do is force somebody to move around that grid in a way like, for instance, the railroad map that I showed you earlier, where it has been demonstrated that, in fact, recalling the image of something that is further away from San Francisco takes longer when you're anchored in San Francisco cognitively. Okay? Pavio has done a number of studies in this area, as I said earlier. But they've been able to demonstrate, for instance, that recall of concrete words is better than recall of abstract words for some very obvious image-related issues, if you think about it for a minute, okay? Concrete words basically refer to touchable, real-world events, concepts, objects, okay? Things that have a direct physical representation. They're easily imaginable. When I mention a particular object, you can conjure up an image of it very easily. Those are words that have high imagery value. For instance, cat. Cat makes it easy for you to imagine something. Now, you may not imagine a tiger, but that is, in fact, a cat. That was the only image I could find on the internet when I needed it. But cat is a high imagery value word. So is dog. Okay? You don't have any trouble with that. That is my graphic glory. That's the best I can do graphically, so enjoy it while you may. Here's another one. I really went bananas on this one. My son's penchant for Corvettes clearly shows up there. Those are concrete words, all three, easy images. Okay, so they are also described as high imagery value words. Let me show you another example, though, still on screen. Less obvious real-world anchors occur when I give you something like truth. Truth is a problem. We can very precisely define it. We can give you examples of it. But that is an abstract word. For the 50 people in the room here, there are 50 different images that you're working on at this point. because truth does not suggest an image as obviously as cat or cigarette does. Okay? You want another one? Justice. Same thing. It just kind of goes away when we try to come up with an image. Okay? And then we get back to the American way. Okay? And that brings in a third image up, Superman. All right? Imagine a cigarette. I'm going to use this image since I took the time to create it. We got a match. We're going to light it. Takes us a minute, but we eventually, a little draw, and we eventually get that sucker lit. And then it's going to be, got the match out. And now imagine this cigarette, 25% smoked with a 1/4-inch ash on it. I'm going to bet your ass you can do that. See, when I got into it, I was really on a roll. But what you're seeing there is essentially the richness of imagery, okay? And it is possible to ask a question then about how that imagery really influences the operation of recall. Do we use images like that to try to retrieve verbal information? And therein lies the basic argument that has led to Alan Pavio's proposal of what is called dual code theory. That is so complex, I'm not going to get into it at this point. We'll start the next lecture with it. But in essence, the setup there is what I was doing, and that is the battle between images as a source for retaining information versus words. We'll pick it up there next time.